last lecture in condensed matter course. We're going to continue discussing superconductivity today, and we turn to slightly more practical uses of theory in the quest of understanding superconductivity. The plan is to, the first half of the lecture, to present what is known as Bogoliubov-deGennes theory of superconductivity, which is basically a more modern version of the BCS theory, which allows understanding of superconductors at finite temperatures and also in non-uniform situations. And overwhelmingly, if you read any papers about superconductivity written more recently, then this is the formalism that is being used. And in the second half of the lecture, I will talk about a phenomenological approach, the so-called Ginzburg-Landau theory of superconductivity, which is actually based on the free energy that you had, I noticed, written on the blackboard in the previous lecture, which I think there went under the name of Higgs theory, but it all is the same. So that one allows, again, for relatively straightforward understanding of electromagnetic phenomena in superconductors, and we will derive some of these from Ginzburg-Landau theory. Okay, so Bogoliubov-deGennes starts from the same BCS reduced Hamiltonian as we studied yesterday, but instead of looking laboriously for the ground state, we solve it by performing a mean field decoupling, similar to Hartree-Fock, and then we diagonalize the resulting bilinear Hamiltonian through a canonical transformation. So this is a kind of combination of Hartree-Fock type theory and Bogoliubov theory for liquid helium that we studied earlier on. So this proceeds by defining an operator B of L as a product of these two guys, and this then will be B dagger of K. And then we do a mean field decoupling where we replace a product of these two operators by the following: B dagger dl plus B dagger K dl minus the expectation value of the two. Okay, so this is like the Hartree-Fock theory that we studied about 2 weeks ago. And this is not exact. Once again, this neglects fluctuations and quantum fluctuations in these operators. But in fact, just like in the theory of superfluid helium, in thermodynamic limit, this decoupling actually can be shown to give you exact ground state and very good approximation for all the excited states. Okay, so when I do this, of course, this term here remains unchanged. This interaction term is replaced by something like this. And what I'll do, in addition, I define the following quantity. I define quantity delta K, which is minus sum over L VKL, expectation value of dl, which is simply sum over L VKL, an expectation value of C minus L down C L up. Okay, and you can see that with the help of this quantity, I can rewrite this Hamiltonian in the following way. So this is what in the literature people call H mean field, which is a mean field approximation to the full reduced Hamiltonian. The kinetic energy remains the same, so I just copy it. But the interaction term now looks like this. Sum over k, delta k, C dagger k up, C dagger minus k down, plus delta star k, C minus k down, C k up, minus delta k times the expectation value of d dagger k. Okay. So now the Hamiltonian is bilinear in my fermionic operators. This is just a constant term, and I can diagonalize it by what is known as Bogoliubov-Degennes transformation.
Whether Bogoliubov-Degennes is the same as Bogoliubov-deGennes.
Yeah, so I was just going to comment on that. Bogoliubov wrote this down first for bosons. I think Degennes wrote it down first for fermions. And what Degennes did, Degennes generalized this to spatially non-uniform Hamiltonians. Basically, he wrote it in real space. And that's why I suppose this should be called Bogoliubov-Degennes theory, but in the literature you just find Degennes being omitted. I think he wrote it first in momentum space for fermions, but Bogoliubov was the first to write this type of transformation for bosons. So this transformation looks like this. We write Ck up as U star k gamma k up plus Vk gamma dagger k down, and similarly C dagger minus k down as minus V star gamma k down plus U k gamma dagger k up. So instead of our electron operators, we define a new set of fermionic operators, gamma k up, gamma k down, and some, at this point, unknown coefficients. It turns out that if we require that this is a canonical transformation, namely that gamma k sigma has the proper anti-commutation, obeys the proper anti-commutation algebra, delta k, k prime, delta sigma, sigma prime. This then implies requirement that uk squared plus vk squared is equal to 1. As you can imagine, these u's and v's will turn out to be the same u's and v's that entered the BCS wave function yesterday. And however, this formalism will allow us to define them even at non-zero temperatures. And this will be useful because, of course, we want to understand superconductivity at non-zero temperatures. Yes, thank you. That should be dagger. Yeah, without the dagger, they should be equal to 0. Okay. So now you can imagine how this proceeds. It's somewhat similar to what we did in the case of Bogoliubov theory for liquid helium. I simply take this transformation and plug it into this original Hamiltonian, and then require that the coefficients u and v subject to this constraint are such that the new Hamiltonian is diagonal. So let's do that. This is slightly laborious, but I skipped some steps yesterday, so let's do this so that we have some we earn our pay today. So this is how it looks. So this is what happens just to the kinetic energy term. And then there is another equally lengthy expression for the interaction term. But let's persist here and let's keep writing. Okay, so this is probably the longest equation of the course. But again, there's no rocket science here. We just substitute, again, this in there and gather the like terms. And now we can inspect this Hamiltonian. And we see that terms in lines 1 and 3 are good because they are already diagonal. This is the Hamiltonian that we want, right? We want something that has a form gamma dagger k, gamma k. That's a diagonal Hamiltonian. However, terms in lines 2 and 4, those are the terms that we want to not to be there. This should be a dagger here. So these guys, right, and of course this, those have anomalous terms that have either dagger-dagger or Hermitian conjugate, which just have gamma-gamma. So we want those to vanish. And for that reason, we insist that when we combine them, this one with that one, the resulting coefficient leads to 0, right? So we require the following equation to be satisfied: 2 psi uk vk plus delta star k v star k minus delta k. Sorry, this should be squared. Squared is equal to 0. So what I'm doing, I'm basically taking psi of k times twice this, and then adding to it this combination here, and setting that to equal to 0. That will ensure, if I can satisfy this condition for these coefficients uk and vk, that will ensure that these underlying terms drop out. And you could do the same thing for these Hermitian conjugate terms, but that would lead to the same equation, just complex conjugate. So it's the same equation. Now, the way to solve this equation, one way is to multiply both sides by delta k star divided by uk squared, and something useful will happen when I do that. I will isolate then this term and put everything else on the other side, and what I get then is delta k star vk over uk, and this is equal to square root of psi k squared plus delta k squared minus psi of k. And if I define this quantity as before as my E of k, I can write this as ek minus psi k. Okay. So there's a few things that I can notice. I notice that the right-hand side is real, right? Because this psi k is just energy dispersion minus the chemical potential. That's real. The square root is real. So this tells me that this combination of uk and vk is also real. And therefore, what I can do without any loss of generality from now on, I can choose uk to also be real. And then vk will have the same phase as delta. So from here, vk has same phase as delta k, right? So this is just one phase convention that I can use, but this is a useful one because one of them is real and the other one has the same convention as this delta parameter, which I still have to determine. Okay, so basically what I can now do easily, I have two equations for two unknowns. This is one, and I have this condition here, which is the other condition, and they are actually easy to solve. One way of doing that would be to simply take absolute value of both sides and then solve for u and v. And the result as, so let me call this 2, and let me call this 1. And let me just say that 1 plus 2 implies the following solution for my problem. uk squared is 1/2 1 minus psi k over ek, and similarly vk squared is 1/2 1 plus psi k over ek. And if you don't see right away that this is the solution, I invite you to plug this in and check. Indeed, you can trivially check that when you add them up, they add up to 1. That's easy to see, but also it's easy to see that when you substitute that into the left-hand side of the second equation, you get the right answer. So this is the same as BCS. Which is reassuring. And also this buys us some extra possibilities here, because we now not only have the ground state of the system, but we have a Hamiltonian that we can use to study the excitations of the system. So basically, what's our Hamiltonian? Well, we have to look back here. So we chose our coefficient so that this guy and this guy vanishes. This is a constant, so this will stay. But our Hamiltonian basically consists of this piece, and this constant here. And all we need to do is to massage this a little bit. We put our result that we obtained for u and v into here and get the final mean field Hamiltonian. And it can be seen to have the following form. After this operation, it's sum over k and sigma ek gamma dagger k sigma gamma k sigma. So this is the operator content. And then there is a constant piece which looks like this. Psi k minus ek plus delta k b dagger k. And this ek is defined there, but let me write it again. Ek is a square root of psi k squared plus delta k squared. So this is the part that describes the excitations. And this is the part that describes the ground state energy, Es. And if you compare with the expression that we derived for the ground state energy yesterday from our variational approach, this is precisely the same. So basically what this, again, affords, this Hamiltonian, is understanding of the ground state as well as the excitations above the ground state. How do we see that these are excitations? Well, this is easy to see. These energies here are all non-negative. In fact, they are all positive when delta is non-zero. So clearly the ground state is achieved when I have none of these states occupied, right? The ground state would be the vacuum of, in terms of these new gamma operators. Yes? Say it again?
Is it possible to solve the excitation problem of BK diagonal?
Sure, yeah, and we will do that. Yeah. So anyway, the ground state is simply the vacuum of gammas, namely the ground state satisfies the condition that gamma k sigma psi g is equal to 0. Okay, so basically we can now write the Hamiltonian as this piece plus a constant, and we know everything about this Hamiltonian because this is just a non-interacting gas of fermions with these excitation energies. It also now should be clear why this delta k has a meaning of excitation gap. Well, if psi of k goes to 0, which would normally be the lowest lying excitations in the normal state, then if delta is non-zero, then this becomes the lowest excitation energy. In order to make this solution valid, we still need to close the loop in the sense that this delta here is also an unknown quantity at the moment, right? This delta has been defined over here as an expectation value of BL summed over all of these variables, over all the momenta multiplied by the interaction, or in other words, like this. So we can now express it, we can now actually calculate it. So the way we do that, once again, and you can imagine how we do that, we take the Bogoliubov transformation here, and we substitute for these C's in here, and express this expectation value in terms of these gammas. And that's going to be easy because the Hamiltonian is diagonal in those gammas. So we know how to do that type of calculation. So let me just do that. Delta k is minus sum over L, VKL, C minus L down, C L up. I substitute for those CLs from the Bogoliubov transformation, and what I get is the following: minus sum over L, VKL, 1 minus gamma dagger k up, gamma k up, minus gamma dagger k down, gamma k down. And I'm recognizing that the mixed terms, such as gamma dagger k up, gamma k down, they're all 0 because they don't appear in the Hamiltonian. right? So only the expectation value of the terms that appear in the Hamiltonian have in the ground state or in the excited state have a non-zero expectation value. Now, in thermal equilibrium, just as for the ordinary electron gas, the expectation value of gamma dagger k sigma will be given by simply f of ek Fermi-Dirac distribution function, which is just this. So I can now substitute for this in here, and what I obtain is the venerable BCS gap equation now at, oh, I'm sorry, I'm just missing something, and I apologize. So what I'm missing is factors UL star VL. Okay, they should also be there because when I perform this substitution, each gamma comes with some of these factors. Okay, so here's the BCS well, yeah, this is basically the same as BCS gap equation, but written at a non-zero temperature. VKL UL star VL 1 minus twice F of epsilon L. And maybe you met this type of combination of one unity and twice the occupation factor. It can be actually written as a hyperbolic tang. So should I? Yes. Okay, this is because this should all be L's. Right, these guys have L index, so this should all have L. Yeah, thank you. That's a very good point. So all, yeah, I'm summing over L, and there's L everywhere, so all these should have L's. So this can be rewritten, and I hope you can still see that, as minus sum over L, VKL. Now, UL star VL, I can express from my solution for U and V, and this is simply delta L over twice EL, and this part here can be written as hyperbolic tangent divide of beta EK over 2. So this is the equation which is equivalent to the BCS gap equation. Okay, so let's solve the BCS gap equation. Which again is that last equation that I wrote. And again, we make the usual Cooper ansatz. That VKL is equal to minus V close to the Fermi level, and this then implies, as yesterday, that delta K is equal to delta, a constant, again, when K is sufficiently close to the Fermi level, and I will not rewrite all those conditions here, but once I've done that, then the BCS gap equation turns to the following. Delta over V is equal to 1/2 sum over K with this prime, where this prime means that my summation is only allowed over a range of momenta close to the Fermi surface as before. And then I have tang 1/2 beta ek divided by ek, and I should have delta here as well. So once again, as before, this equation has a trivial solution. Delta is equal to 0. In that case, we just go back to the normal state. It's just a simple metal. What we're interested in is a non-trivial solution. Namely that delta is non-zero. In that case, we can cancel it out from both sides. We can divide by it and write the BCS equation in the following form. I rewrite it now as an integral. As usual, the right-hand side can be rewritten as an integral, and it becomes the following. Okay, as usual, I now perform, so this is my density of states. I now perform the usual approximation that I can approximate this by the density of states at the Fermi level, in which case I can pull this out in front of the integral, and I have the final form of my BCS gap equation. So for a moment there, I was wondering where did this 1/2 go? I thought I forgot it, but no, this integral here would normally go from minus h bar omega c to omega c, and there would be a 1/2. But since it's even in the psi variable, I can just integrate over half of that interval and get rid of the 1/2. So actually, this is correct. So one can now. So what is this? This is an implicit equation for delta as a function of t, right? So t, of course, enters into this beta, and let me just write it here for those who maybe forgot. Beta is 1 over kBt. Everything else is constant. This density of states, interaction strength, those are all constants. Psi is an integration variable. There is some cutoff h bar omega c, which corresponds to some phonon coupling strength. And in order to satisfy this equation at a given temperature, there will be some value of delta T that might satisfy that equation. Okay? And what one can do, one can just, these days it's not difficult to solve that equation numerically. And it has the following behavior as a function of temperature, you would find that starting at 0 temperature, it will basically not do much. It will be a constant, and then at some point it will start going down, and then it will reach 0 at a critical temperature Tc. Right? So one can now solve it in a number of different limits, and so this would be a numerical solution. And by the way, the best way or easiest way to solve this numerically, if you want to do that one day, is to restore this delta, right? Is to put this delta on the right-hand side and left-hand side and simply do a dumb iteration. So you start from some value of delta that is non-zero, and you write this delta is equal to the right-hand side, and you just keep iterating until things stop changing, and you know you can get that curve in under 1 second if you want on a simple laptop computer. Okay, so a few limits that one can solve. So at t equals 0, one can solve this, and it basically becomes the same equation that we solved yesterday. We had that equation on the board. Basically, this just becomes a step function, and we found the solution yesterday, so I will not reiterate. I will just write the result. So this is delta at 0 temperature, and one gets 2h bar omega c e to minus 1 over n naught times v. If you take notes, then at the end of yesterday's lecture, we showed that. What we couldn't show, or what we can do that is new here, we can solve it now for Tc, what is the value of the critical temperature. And so determination of Tc. Basically, Tc is determined by delta going to 0, right? So we expect that delta at Tc will go to 0, which means that Ek goes to simply psi of k, right? Ek is defined over there as psi of k squared plus delta squared square root. So we can simply solve this equation for Ek replaced by psi k, meaning just taking this delta to 0. And this equation actually can be solved in this limit like this. One just gets integral from h bar omega c divided by kbt dx tang x over x, where I defined a new variable here, x. What was my x? Was just basically 1/2 psi over kbt. And this is an integral that one can actually compute. And this integral has a value of log a beta h bar omega c, where a is 2 gamma over pi. Gamma is the Euler constant, and this is roughly equal to 1.13. And this is just a mathematical fact. We don't have to worry about that. So once again, what I want to know what is the temperature at which this happens, right? So I want to solve this equation for beta, or for the appropriate temperature. And what one gets is that KB TC, which is 1 over beta C, becomes 1.13 h bar omega C times e to minus 1 over n naught b. Okay? So all I'm doing, I'm just taking an exponential of both sides of this equation and then solving for 1 over this beta. And this is the expression for the critical temperature. So this is okay. So we see once again that the critical temperature of the superconductor is related to the phonon cutoff, h bar omega c, and again has the same non-analytic dependence on the density of states and the interaction strength as the expression for the superconducting gap at 0 temperature. So again, there's no hope of getting this in any sort of perturbation theory. One has to do this type of non-perturbative calculation. Now, a very nice and experimentally testable quantity is the so-called BCS ratio, which follows from dividing this one with that one. Okay, so this is the so-called BCS ratio. Delta naught divided by KBTC. And this is just a pure number. It's 2 divided by 1.13, which is roughly equal to 1.764. Let me put a nice purple frame around this. So this was one of the great early successes of this theory, because this ratio, you see now, doesn't depend on anything, right? It does not, I mean, in principle, if you know about phonons in the material, if you know the interaction strength, you can predict TC and delta separately. In practice, this is difficult because in a solid, these things are not so easy to measure. However, the theory makes this unambiguous prediction that when you measure these two quantities, delta naught and TC, and you divide them, you should get a number that is, something, right? So this can be easily tested. And indeed, this has been tested, and in known superconductors, experimentally, experiment finds this ratio to be in the range between 1.5 and 2.3. So this has been a great success of this theory, and of course it had other successes. Yes? Yeah, so in a sense, so this applies to what we may call conventional superconductors. Conventional low T superconductors, such as lead, aluminum, niobium, dozens of them that have TCs on the order of few Kelvin, 10 Kelvin or so. There's also so-called unconventional superconductors, in which we don't really understand the mechanism behind superconductivity, and high TC cuprates are the kind of flagship unconventional superconductor. And in those, these values can be as high as 5, which tells you that this theory does not really seem to apply to them very well. Yes?
So what causes these fluctuations in BCS or 5?
If you ever try to predict something in a solid, you would be astonished how fantastic this agreement is. One could, I think that question would be better phrased as asking, how come that these fluctuations are so small, right? I mean, each solid is a bit different, right? We have used a very simple model for a solid, just a free electron gas with some interaction that is kind of slightly artificial. So from that point of view, it's extremely surprising that these experimentally measured values are so close to this theoretical value. Yeah, so there's actually, there's an industry of people actually trying to predict TC and delta naught separately, right? To estimate these parameters and you know, get a material, do a band structure calculation, do a calculation for phonons, estimate the interaction strength, and try to get these, you know, not just the ratio, but the actual values. Now, in the history of superconductivity, nobody ever succeeded in predicting this with any degree of accuracy, right? And this is simply because this exponential dependence, you make a small mistake in this V, which is very easy to make, and it's in the exponent, and it just multiplies like crazy. And what you thought would be a 20 Kelvin superconductor can be a 20 millikelvin superconductor if you make a factor of 2 mistake in this, right? So this is extremely difficult game, and it's very hard to predict TCs for superconductors precisely because of this exponential dependence. The nice thing about this ratio is that it just drops out, and then, you know, these two quantities actually correlate, and that's a very strong prediction of the theory, which has been observed experimentally. Okay, so I still have lots of material to cover. So let me just make a few remarks about the consequences of this theory at finite temperature. So it predicts excitation gap. And this gap is delta T absolute value. And this gap can actually be measured in a number of measurements. A classic measurement of this excitation gap is the optical, it's tunneling and optical absorption. So let me talk about optical absorption because it's more easily understood. So basically, you take a piece of material that is a superconductor and you shine light on it with frequency h bar omega, and you study how much is absorbed and how much is reflected, right? Now, in a superconductor, the density of states looks like this as a function of energy, epsilon. If I plot density of states, it's 0 below delta, and then it grows. Well, in fact, density of states actually looks more like this. It has this singularity here. But anyway, density of states is exactly 0 in the range between 0 and delta, just because there are no states. That's the meaning of the gap. So if you try to shine light on the superconductor with the energy inside the gap, then there's no absorption. So there's no absorption for h bar omega less than delta. Actually, yeah, for reasons that I don't want to go into, it's actually 2 delta, but this is well understood. And so optical absorption is a direct measurement of the superconducting gap, and that's one way how one can test these predictions, measuring the gap. TC, of course, is easy to measure. You just hook electrodes to your superconductor, and you see at what temperature it goes into a 0 resistance state, whereas the superconducting gap can be measured like this. One can easily calculate thermodynamic quantities, and let me just mention this one last thing. Specific heat jump. And we calculated specific heat of phonons and electrons. So in the same way, one can calculate it for this system, because the Hamiltonian we have the excitation spectrum. So I will not do that to save time, but I will just sketch the behavior, which is a characteristic of a superconductor. So this is CV as a function of temperature. And as a reference, let me draw a straight line, which would be a specific heat of the normal metal. So I disallow superconductivity. I just don't include those interactions. Technically, I take delta equals 0, and then the specific heat of a electron metal just goes linearly with temperature at low temperatures, as we discussed. Now, this is changed in the superconducting state, and if this is my Tc, let me just draw a dashed line. The specific heat, when you calculate it, and it's not a difficult calculation, actually looks like this in the superconducting state. So first of all, at low temperatures, specific heat is activated here. So instead of linear, it goes as e to minus beta, or e to minus delta over kBT. And this is because you have an energy gap, right? So you're raising temperature, and there's no states that you can excite with any probability. So the specific heat is initially 0. Then you start seeing some pickup because of the Boltzmann factor. And then the area that you lose here is actually recovered under this peak. And this is the famous jump measured in specific heat of superconductors called delta C. And this jump, again, has a universal value. You can calculate this jump in specific heat divided by Cn, where Cn is this value here. So this would be a value of the specific heat in the normal state. And it's 1.43. Again, it's one of those integrals like that, and it's just a number. And once again, this is a quantity that is, I wouldn't say easily measurable, but has been measured many times, and experimental values cluster, again, within 10–20% of this value. So this is another successful prediction of the BCS theory of superconductivity. And there's many others, and just like QED is one of the most successful theories in kind of fundamental physics, so is BCS in solid-state physics. Okay, any questions about this? I'm going to switch gears, and in about last half an hour that we have, I will discuss some electromagnetic properties of superconductors based on Ginzburg-Landau theory. And this theory was first developed by Ginzburg and Landau in 1950. It was first developed as a purely phenomenological theory of superconductivity, but later on it's been shown that it can be derived actually from the BCS theory in the appropriate limit. So the idea is to describe Cooper pair condensate by a complex wave function psi of r, which has an amplitude and a phase. And they can both, in principle, depend on space. And then psi squared is identified as the condensate density whereas phi is the condensate phase. And the fact that it's a complex wave function will have important consequences. This condensate wave function is subject to Ginzburg-Landau free energy functional, which has the following form: is an integral d3r of 1 over 2m star p minus e star over c a psi squared plus 1/2 alpha psi squared plus beta psi to the fourth, where A is the vector potential of the applied electromagnetic field. M star is approximately 2me, and E star is 2e, mass and charge of Cooper pairs. Alpha and beta are known as Ginzburg-Landau phenomenological parameters. They are material dependent and have the following behavior. Alpha can be expressed roughly as alpha naught times T minus Tc, whereas beta is, to the first approximation, temperature independent. And so the chief virtue of this Ginzburg-Landau free energy functional is that it allows a convenient description of electromagnetic properties of a superconductor, namely when this vector potential is non-zero, and we will show some examples of this. So basically what you want to do, you want to take this free energy and minimize it. You want to find this condensate wave function that, for given parameters here, minimizes the free energy, right? So the game here is find psi that minimizes f of psi. Namely, we take a variational derivative f psi with respect to psi star and set it equal to 0. And this then leads to the famous Ginzburg-Landau equation. And the Ginzburg-Landau equation looks like this: 1 over 2m star p minus e star over ca psi plus alpha psi plus beta psi squared psi is equal to 0. So this is like a nonlinear Schrödinger equation. If we didn't have this third term, this would look like a Schrödinger equation for a particle in a vector potential psi, and this should be squared here in vector potential A. But this is a nonlinear system, so it's a nonlinear Schrödinger equation. One can solve this to see that it has any merit. Let's just solve it for the uniform case. So we set A equal to 0 and no fields, and assume psi is a constant in space. In that case, A is not there, and if psi is constant, then P doesn't really do anything because P contains derivatives. So I'm just solving this, the last two terms. So I get A psi plus beta psi squared psi is equal to 0. Again, trivial solution is always possible. That corresponds to non-superconducting state. Cooper pair condensate is 0. But when a non-trivial solution exists, then I can cancel this out and solve for psi squared. And from this, I get that psi is equal to square root of minus alpha over beta. This looks kind of bad with this minus sign, but notice that this alpha is chosen such that it's actually negative for temperatures less than Tc, right, and positive for temperatures greater than Tc. So I can substitute that, and I can obtain alpha naught over beta Tc minus T. And if I plot this, then it basically has the expected behavior like this, where this solution exists when temperature is less than Tc in this range between 0 and Tc. And then it has this profile, whereas above Tc, this would be imaginary. So only trivial solution exists above Tc. So at least crudely, this has the right type of behavior for the uniform system. So what can we get out of this that is interesting? Like I said, what's interesting, or why this is useful, is electromagnetic properties. So what we're interested in is the supercurrent, in other words. And the supercurrent can be obtained from this by minimizing the free energy, or the supercurrent can be defined as a variational derivative of f psi, now with respect to A, the vector potential, right? And you've seen that in your field theory course probably. And when you perform this variational derivative, it can be written as follows: E star over M star psi squared H bar gradient phi minus E star over C times A. Okay, this is the supercurrent based on the Ginzburg-Landau equation or Ginzburg-Landau free energy. And this is actually a very important equation because it says something immediately that is somewhat unusual. So what this implies is that J, your electrical current or supercurrent, is proportional to vector potential directly, right? And you can now argue that this is not gauge invariant, but actually it is, because under gauge transformation, this phi also transforms properly. So this is gauge invariant. Gauge invariant sends A to A minus gradient of some lambda, and it also sends phi to e to I lambda times phi. And in other words, it shifts this phi, and therefore this term actually is gauge invariant as required for the current. So everything is fine, and this leads to some very interesting consequences that are physically observable. What we will further do to simplify things, we will use the so-called London approximation. Where we take this equation, but we just disregard any variations in this psi. So London approximation consists of replacing psi squared by ns, which we take to be constant. So in the London approximation, J is simply E star ns divided by M star H bar gradient phi minus E star over C times A. This is not crucial, but it simplifies things, so I will just use the London approximation to derive a few things. So two things that one can get very easily from this Ginzburg-Landau approach is the Meissner effect, which is the kind of defining property of a superconductor, as well as flux quantization, which is another neat manifestation of superconductivity. So let's see if we can discuss both of them. Meissner effect is the expulsion of a magnetic field from the bulk of the superconductor. So let's study the following situation. Let's consider a half plane or half space for x larger than 0 to be filled with a superconductor, and on the other side there's a vacuum, right? And what we want to apply magnetic field here in the vacuum, and we want to see how it evolves as we hit the superconductor, okay? So the way to address this is to take first a curl of the London equation, and you can see what happens. This is just constant. Curl of a gradient is 0, so the first term doesn't contribute, and the curl of the second term, A, is just a magnetic field. So I will find that curl of J is minus E star squared ns over M star C times B. Okay? Everybody with me? So again, just curl of this term is 0, curl of A is B by definition, and so I get this simple relation. Now there's another equation that connects B and J, which is Ampere's law, right? I can write Ampere's law and Ampere's law, just one of the Maxwell's equations, connects curl of B with 4 pi c over J, right? This is just the second Maxwell's equation. And I can now solve these two simultaneously, right? This Ampere's law is always valid. This is valid in a superconductor. So when I want to solve in the superconductor, I can combine them. And one way of doing that would be to take another curl of this, right? Then I get curl of B here, and I can replace it with J, or rather what I want something for B. So so I'm sorry. I want to take a curl of this, I get curl of B and then curl of J on the right-hand side, and then I replace it with this. So let's do that. I get C over 4 pi curl of B is equal to curl of J, and I immediately replace it with this. So I get minus E star squared NS over M star C times B. But there's an identity for curl, which tells me that it's a gradient of a divergence minus Laplace. B is a divergence-free field. So this thing here turns out to be minus Laplace of B. Okay. So I end up with the following equation. I end up with equation Laplace of B is equal to 1 over lambda L squared B, where I collected all these coefficients into this lambda L, and lambda L squared is defined as M star C divided by 4 pi E star squared NS, and is known as the London penetration depth. So I was hoping that I could finish it on that side of the board, but maybe not. So let's now solve this equation for magnetic field for this geometry, right? So what I have a field pointing along the z direction, and I apologize, I cannot erase this because I came to the end of the board, and it depends on x, right? So I want x dependence. So let me solve this. So I have B that is some function of x, and it's in the z direction, right? So the Laplace I can replace simply by second derivative with respect to x of this B function is 1 over lambda squared B. And the solution to this is actually quite simple. It's Bx is B0 times e to minus x over this lambda L. Okay? So in other words, magnetic field decays exponentially inside the superconductor, and the decay length is the London penetration depth, which is in various materials. If you calculate or measure this lambda, it's on the order of 100 to tens of thousands of angstroms. So it's a microscopic length scale in various superconductors. So basically what I have in terms of this picture, outside the superconductor, I have a constant magnetic field, and as I hit the superconductor, it decays to 0, where the decay length here is lambda of L. And again, that's just hundreds or thousands of angstroms. So if I look at the macroscopic superconductor, then basically in its bulk, the magnetic field is 0. And that's the Meissner effect. You can ask, how does this happen? How does the superconductor do this? Well, it sets up screening currents. Clearly, this screening current J, there's some current going on here because curl of B is equal to J. So the superconductor sets currents that create field that is exactly opposite to the applied magnetic field. Shielding currents. And one can solve for the current as well. Let me just write the result here. In this geometry, the current inside the superconductor would be along the y-axis. There would be some J naught, and then it would decay exponentially also into the bulk. Okay? And again, as I said, this is the defining property of a superconductor. This was after the zero resistance that was measured by Kamerlingh-Onnes. This Meissner effect was basically the second important discovery about superconductors. Any questions about this? So the last thing I want to tell you about is the flux quantization, which is another neat thing. So imagine a multiply connected geometry So imagine I make a ring out of a superconductor so that there is a hole here. And I ask, what is the magnetic field here that is allowed to go through this hole? And it turns out it's actually quantized. I cannot have any flux going through that hole, but the total flux is precisely quantized. So how can we show that? This is actually very easy to show, and it's done like this. Imagine I take a path that goes inside the superconductor. I start at this point, or let me start here, but it's deep inside the superconductor. And then I go around and around, and I come here, and I call this path C. Okay, and it's important that that path stays away from all the edges. So it's beyond any screening length like this. For a macroscopic body, that should be easy to attain because the magnetic field really penetrates only microscopically deep. Now, because of this, we found that all these shielding currents decay exponentially with this microscopic length scale. So I expect that J is going to be equal to 0 along path C deep inside the superconductor. Okay? So now let me take this equation here and let me examine what does it mean that this J must be equal to 0, right? So first of all, so when I set this equal to 0, these constants here are non-zero. So the only way this is going to be true is if this bracket here is 0, right? So J equals 0 immediately implies that HC over E star gradient of phi is equal to A everywhere along that path C, right? So again, I just set that bracket to 0 and took A to the other side and divided by the constants. Let me now take this equation, and since it's valid everywhere along that path, let me take a loop integral dl along that path, and let's see what happens here. So h bar c divided by E star, I just copy, and here I have integral dl along the path C dotted into gradient phi is integral C A dot dl. Okay, So let's examine first the left-hand side, right? So what I have here is an integral over a closed path of a gradient of a function, right? So naively, you would think it's a 0 because when I just integrate, I would get phi at the end of the path, let's call that L, minus phi at 0. But since it's a closed path, these two should be the same, so it should vanish, right? However, this is not necessarily so. All I require is that the wave function psi equals psi times e to the I phi is single valued. And this permits phi to have a net winding around this hole that is 2 pi times s, where s is an integer, right? So if I start from this point, and let's say my phase is 0, and I go around and end at the same point, and my phase is 2 pi, then this thing is still perfectly continuous and single valued, so that's allowed, right? So I can advance my phase by any integer multiple of 2 pi, which means that this integral here actually can be equal to 2 pi s, where s is an integer. Okay? Does that make sense? And 0 is one possibility because s equals 0 is also allowed, right? So now what about the right-hand side? Well, right-hand side I can manipulate using the Stokes theorem. I can integrate d2s over the area that is bounded by this path and integrate curl of A, right? And what this is just a magnetic field, right? And area integral of the magnetic field is just the total flux, phi. So the total magnetic flux through the hole, I conclude, is equal to 2 pi s hc over E star, which typically would be written as phi naught times s, and s is an integer, and phi naught hc over 2e is the superconducting flux quantum. Okay, so what this tells me is that in a multiply connected geometry like that one, magnetic flux is precisely quantized. The unit of quantization is this combination of fundamental constants, Planck constant, speed of light, and charge of electron. 2e comes in because it's a condensate of Cooper pairs, each have charge 2e. And allowed fluxes through this are just integer multiples of this fundamental flux quantum. This has been measured early on in the so-called Little Parks experiment. Which, again, was another spectacular confirmation of this theory of superconductivity. To date, this quantization is exact. As far as we understand this, this is exact, meaning there's no corrections to this. So this is not well known, but there's a compendium of fundamental constants, the best measured values of fundamental constants like Planck constant, speed of light, charge of electron, and so on. And you would think that these come from some fundamental measurements, right? I don't know what, but it turns out that the most precise measurements in existence of, I think it's Planck's constant, come from precisely measuring this flux and using it as a definition. So imagine you could, in some other way, precisely measure C and charge of electron, right? And then you want to measure H, Planck constant, and then you decide that your most precise way of doing that is measuring actually flux through a hole in a superconductor, dividing out C and E, and getting the value of H. And it turns out if you look into this, every 5 years, there's a new compendium of these most precise values of constants. And it turns out that charge of electron, the most precise measurement, comes from quantum Hall effect, which is the topological state that we discussed previously, where sigma xy is quantized. And the most precise value of Planck constant comes from these measurements. So that's pretty cool for a humble solid, isn't it? I mean, this has disorder in it, right? This can be dirty, and still it quantizes flux in this precise way that we cannot measure anything more precise than that. I find that cool. So with this, thank you. Any questions? Yes?
It is surprising to me that all this derivation is not dependent on the size of the ring. So is it possible, for example, to have one or two quanta, a small number of flux quanta in a macroscopic ring, for example, say 1 millimeter long, for example? Or the number S somehow depends on the size of the system?
Well, I'm not sure I'm quite getting the gist of your question. So as long as the size here, let's call this D, and as long as this is much larger than London penetration depth, this works, right? So let's say if D is millimeters, that's perfect because lambda is hundreds of angstroms. So that's perfectly fine. And then how many of these fluxes you can put in just depends on how large a field you can produce, right? Typical laboratory field of few Tesla, and if this hole is macroscopic, you can put in lots of flux quanta if that's what you want to do. But I don't know if that's what you wanted.
Yeah. I think that's it. I mean, the thing was, if there was some kind of way to measure a small amount of flux quanta in, say, a hole of 1 millimeter radius or something like that. Although, the question was more related about the size of the hole more than the size of the ring or the width of the ring.
Yeah, so the flux is a product of magnetic field and the size of the hole. So in order to measure that accurately, one has to, of course, devise a way how to accurately measure the size of your device and so on and so forth. But those are things that we can do. Question?
This is going to give you the difference between type 1 and type 2 superconductors.
Yeah, so I didn't discuss there's a distinction between type 1 and type 2 superconductors. And since I have 1 more minute to spare, let me just briefly tell you what that is. Type 1 and type 2 superconductors differ in their detailed response to magnetic field. In a type 1 superconductor, roughly speaking, when you apply magnetic field here, then and you increase it beyond some critical value, then basically it destroys superconductivity, and it happens immediately. The whole sample goes normal, and the magnetic field penetrates. Type 2 superconductor have a kind of more interesting response. When you increase magnetic field beyond some value, magnetic field can penetrate, but in a kind of funny way where it sets up these flux tubes. And there's lots of interesting physics about flux tubes, and many of known superconductors are type 2. So that also is actually, that physics is included in this Ginzburg-Landau theory. And if we had more time, we could discuss about these flux tubes and so on. Yeah.
I'm still confused about what we actually do in this experiment. Are we making a magnetic field in the lab and putting a superconductor
Yeah, so you know, you can set it up in a number of different ways. For instance, you don't even have to apply magnetic field because there's Earth magnetic field, which is all around us. So all you can do, you just take this ring, make it like that, and you cool it down to a superconducting, below its superconducting temperature. And if there was some background field, so that there's some flux trapped in this hole, you can then come and measure this flux, right? Whatever it is, no matter how you created it, but you now measure it and you find that it satisfies this equation, that it's always, it cannot be just any flux, it's always some integer multiple of phi naught, right? That's the remarkable thing here. Any other questions? Okay, here.
I mean, I have no idea whether or not this could be done precisely, but this kind of means that, like, if you're cooling a type 1 superconductor below its critical temperature, at some point, if you say had like a non-quantized flux passing through in the phase, as you're cooling it, it kind of like snaps the additional flux either inside or outside.
Yeah.
You actually observe that motion as you pass a critical temperature, or is that true?
That's called basically flux dynamics, and you know, that's also something that has been studied. You know, there's all sorts of interesting physics. This becomes very important because if you, for practical applications, if you ever got MRI done, all the modern MRI machines have superconducting magnets, and that's what allowed this technique to be widespread and reasonably cheap. And so, of course, they deal with strong magnetic fields, and they have superconductors in them, so this sort of dynamics of flux has to be well understood in those, because there would be nothing worse when you're lying in that MRI machine and that magnet would get quenched. It's like a bomb, literally. There's so much energy in this magnet that if the superconductor there went normal, there's an explosion, and you know, you don't want to be there. So basically, people need to understand these fluctuations very well for very practical reasons like that. And there's a whole field of superconductivity which deals with flux flow and flux creep and flux dynamics and all that. I don't know that much about it.
Is the energy in there just that you've got like a massive supercurrent flowing around that goes down?
Yeah, so there's two types of energy. There's just energy stored in your magnetic field, and there's energy stored in this supercurrent. And if you imagine what happens if somehow, so in your MRI, you just basically have a coil of a superconductor, and then you lie inside it, right? And this coil is made out of fairly thin wire, which circulates this huge current. And the nice thing is that once you set up a current in a superconductor, you don't have to maintain it, right? It just flows there. You don't have to pump it up. But imagine one part of this material would go normal, so all this current has no place to go. And what then happens is that the whole wire slowly goes into the normal state and suddenly has resistance. And all this current is now too big to sustain some non-superconducting wire. So it all melts, and basically it just goes kaboom. So that's not good. Yeah, I actually saw somebody's lab after a superconducting magnet did this, right? There was nobody in it, fortunately, but it looked literally like a grenade went off there. So the lab was kind of ruined. So on this note, maybe we should stop because it's lunchtime. So thank you very much, and I hope I see you around.